Okay, class, we're continuing on our chapter of chemical reactions in stoichiometry, and we're going to begin this video lesson by talking about net ionic reactions. By this we mean we're cutting to the chase. We're only going to represent those components that are really reacting, and we'll talk about the concept of spectator ions, those that are just hanging around but are not really involved in the chemical reaction. You know, those characters that come to the dance and they just stand by the punch bowl, eating the corn chips and the salsa, but they're not in the middle of the dance floor actually having fun, right, and actually reacting, doing the nay-nay or the whip or whatever. So let me give you a few examples. Consider acid-base reactions. We've talked about the prototypical acid-base reaction is something like hydrochloric acid plus sodium hydroxide reacting to form a salt, sodium chloride, and water. What we mean by a net ionic reaction is to simplify this, because what is really important here is that hydrogen ion, H+, reacts with hydroxide ion, OH-, to form water. The chloride anions and the sodium cations are just spectators. They're by the punch bowl, munching on the corn chips. They don't know that hydrogen ion and hydroxide ion have come together to form water. A precipitation reaction, similarly, we gave a prototypical precipitation reaction of copper 2 nitrate plus ammonium sulfide. Mix these two solutions together, you form copper 2 sulfide and ammonium nitrate. But actually, this can be simplified if we look at only what is really happening in the middle of the dance floor. What is really happening? It's copper plus 2 cation reacting with sulfide anion to form the insoluble precipitate copper 2 sulfide. The nitrate and the ammonium are still in aqueous solution, diffusing around. They don't know what has happened. Now, to perhaps explain this, look at what I just revealed in the middle of the slide, where I've taken the acid-base reaction and I've drawn it out in all its glory. Instead of writing HCl, HCl-AQ, I've written it as H plus AQ and chloride anion AQ. That's because when a strong electrolyte like hydrochloric acid or sodium hydroxide or sodium chloride is dissolved in water, the cation and the anion are really separated and diffusing independently of one another. So we can represent hydrochloric acid dissolved in water as H plus AQ plus chloride anion AQ. And likewise, sodium hydroxide dissolved in water, we can represent it as sodium cation AQ as if it's by itself, and hydroxide anion as if it's by itself. Now, if we do the same thing with sodium cation and chloride anion for sodium chloride and draw out the complete reaction, what you immediately notice is that chloride anion is on both sides of the reaction, and sodium cation is also on both sides of the reaction. They are spectators. We can cancel them out, and when we do that, we get to the net ionic reaction, which again is hydrogen ion dissolved in aqueous solution plus hydroxide ion in aqueous solution combining together to form liquid water. Now, why do we do this? Why do we talk about net ionic reactions? Well, because it simplifies the reaction, and it's always good just to look at the most important components. So, to give you practice, what would you think would be the net ionic reaction for the following? 2 aluminums, solid aluminum, plus 6 hydrobromic acid, reacting to form aluminum bromide, and 3 hydrogen gases. Write this down, and then when you have time, try to draw out what you think the net ionic reaction is, or perhaps you might want to pause at this point, and then I'll continue to the next slide. For redox reactions, we can also talk about a net ionic reaction. The prototypical redox reaction is that between copper plus 2 cation and zinc metal. We've talked about this before in earlier slides. But really, if we have copper plus 2 dissolved in aqueous solution, there must be some anions, such as nitrate. So the more complete representation of the reaction would be the first line. Copper 2 nitrate, there has to be an anion somewhere, even if it's just a spectator, dissolved in aqueous solution, plus zinc metal. The redox reaction is that in which copper plus 2 becomes reduced to copper metal, and the reactant zinc metal becomes oxidized to zinc plus 2, which will now be balanced by the counterion nitrate. But again, the nitrate anions are just spectators. They're just there to make sure everything is neutral. And if you want to simplify this reaction, it would be what we gave you earlier. That is copper plus 2, Aq, plus zinc metal, reacting to form copper metal and zinc plus 2 cations. The nitrate is just a spectator. Another concept to introduce at this point is the concept of half reactions for redox reactions. This really just applies to redox reactions. So for our latter prototypical redox or oxidation reduction reaction, we can think about this in terms of two half reactions. That is, if we look at copper plus 2 must react with 2 electrons to become reduced to copper metal. That's a half reaction. And then we can also consider a second half reaction, zinc becoming oxidized to zinc plus 2 and giving up 2 electrons. Now, if we have these two half reactions and we add them together, we get the whole reaction, the one we have above. But the reason we talk about half reaction, because that is what is really happening for each of the reactants. Copper plus 2 is finding 2 electrons. Those 2 electrons happen to be coming from zinc, but it's finding 2 electrons to become reduced to copper metal, and zinc is giving up 2 electrons as it becomes oxidized to zinc plus 2. Now, in general, we can write oxidation reactions as shown in the very bottom of the slide. Some reactant, which we will represent in general as O, an oxidizing agent, reacts with electrons, and itself, it becomes reduced. That is, O, the oxidizing agent, becomes reduced. And then if you look at the second half reaction, R, which we consider a reducing agent, becomes oxidized to R plus whatever, plus N in general, and gives up N electrons. I say this because oftentimes in chemistry we refer to an oxidizing agent and a reducing agent. The oxidizing agent will itself become reduced in a chemical reaction, and the reducing agent will itself become oxidized in a redox reaction. Okay? Now in this slide I categorize various types of oxidation reduction reactions. The first type is what can be called a combination or composition reaction. Two things, A plus B, reacting together to form the product C. Now, in many cases, this is some element, A, reacting with oxygen to form an oxide, such as sulfur reacting with oxygen to form sulfur dioxide. Oxygen is very reactive, and it reacts with virtually all the elements in a manner such as this. But also other elements can react together, other A's and B's, such as magnesium can react with nitrogen to form magnesium nitride. Now, either of these type of reactions is actually an oxidation reduction reaction. If we go back to the sulfur plus oxygen to form sulfur dioxide, sulfur becomes oxidized from oxidation number 0 to plus 4, and the reactant oxygen becomes reduced from oxidation number 0 to minus 2. The second general type of oxidation reduction reaction is a decomposition. That is, taking some compound, C, and usually heating it up to split apart the components. A typical example of this would be taking potassium chlorate, heating it up to drive off oxygen gas, and converting it to potassium chloride. Now, if you look at this reaction, it is actually an oxidation reduction reaction. In the left, oxygen has an oxidation number of minus 2. It's the most common oxidation number in a compound. But it becomes oxidized in this reaction as it forms the product oxygen gas, which has an oxidation number of 0. Likewise, in the reactant potassium chlorate, the chlorine, or the chloride, goes from having an oxidation number of plus 5 to an oxidation number of minus 1 in the product potassium chloride. So it becomes reduced in this chemical reaction. It is an oxidation reduction reaction. Something becomes oxidized, something becomes reduced. The third general type of oxidation reduction reactions are what can be called displacement of hydrogen gas by active metals. And here's what we mean by this type of reaction. Calcium can react with water to form calcium hydroxide and give off hydrogen gas. Hydrogen gas will then bubble out as a gas. Now, in this reaction, calcium, the reactant calcium, goes from oxidation number 0 to oxidation number plus 2 in the product calcium hydroxide. It becomes oxidized. Hydrogen in the reactant water goes from oxidation number +1 to oxidation number 0 in the product hydrogen gas. That is, it becomes reduced. So calcium is oxidized and hydrogen ion becomes reduced to hydrogen gas. The oxygen actually stays the same as -2 in both water and in the hydroxide. That's one example of displacement of hydrogen gas by an active metal. The metal calcium can react with water, just with ordinary tap water, to form hydrogen gas. A second example of this is tin, another metal, reacting with hydrochloric acid to form tin chloride, tin 2 chloride, and hydrogen gas. And similarly, in this reaction, the tin becomes oxidized from oxidation number 0 to oxidation number +2 in the product tin chloride. And hydrogen ion and hydrochloric acid becomes reduced to an oxidation number of 0 in hydrogen gas. Something is oxidized, something is reduced. Notice, and we'll emphasize this more in the next slide, that these reactions are similar, but you have to have a stronger reactant, hydrochloric acid, in order to have the reaction occur with tin as opposed to calcium. And we'll see later that's because calcium is a more active metal or a more reactive metal than is tin. The next general type of reaction is a displacement of a metal by a more active metal. And this again, we're going back to our prototypical oxidation reduction reaction. But zinc, the metal zinc, will displace copper cation from copper sulfate to form zinc sulfate and copper metal. Now basically what is happening here, if you think of this as our dance floor analogy, the zinc is a more active player and will eventually wind up with sulfate, whereas copper, being less reactive, would rather be standing by the punch bowl, munching on the corn chips, or in other words, would rather be the elemental form, copper. Zinc is more reactive than copper, and therefore will displace it, with zinc then winding up being in this molecular form, zinc sulfate, and copper becoming reduced to copper metal. So if zinc is a more active metal than copper, is it also true that there are other differences in reactivity, such as the halogens? Yes, chlorine is more reactive than bromine and iodine among the halogens. So, consider the second to last reaction, where we have chlorine gas reacting with potassium bromide. Chlorine is a more active player, and if it sees an opportunity, will move in and will displace bromide, converting bromide to bromine, to liquid bromine. So chlorine can then hook up with potassium to form potassium chloride. Again, chlorine is more reactive and wants to be in a molecular form, whereas bromide or bromine would rather be in the bromine form if given the chance compared to chlorine. So chlorine is more reactive than bromine. The very last type of oxidation reduction reaction on this slide is what is called a disproportionation. That's a mouthful. And this is a complicated kind of oxidation reduction reaction. It might look simple, but it's a little bit more complicated. But because in this reaction, the oxygen in the reactant, which is hydrogen peroxide, actually goes two ways. That is, if you notice there has to be at least two oxygens here in the reactant. One of the oxygens becomes reduced and the other becomes oxidized in our products. That is, in the reactant, hydrogen peroxide, the oxygen has an oxidation number of -1. If we look at the products, in oxygen gas, it has an oxidation number of 0. So it has increased in the positive value. It's become oxidized. Whereas in water, the oxygen has an oxidation number of -2. So oxygen becomes reduced in forming water and becomes oxidized in forming oxygen. Disproportionation, the oxygen goes both ways. Some of it becomes oxidized and some of it becomes reduced in a chemical reaction. A little bit more complicated than you might have thought. All right, so we talked about some metals being more active than others and some halogens being more active than others. This slide shows you what is called the activity series of metals and halogens. Let's talk about the metals first. And this is useful information for you to always keep up with. At the very top left of this table, you'll see what are called the very active metals. And those tend to be the ones in group 1A and 2A, potassium, sodium, lithium, and then calcium, and then slightly below that, magnesium. These are very reactive metals, so reactive that they even react with water, even cool tap water. You've probably seen demonstrations of dropping some potassium or sodium into a beaker of water and how it burst into flames. Potassium, sodium, lithium, very, very reactive, even reacting with water. And then we have a set of metals which are less reactive: magnesium, aluminum, zinc, iron, tin, lead, and it goes in that order. Less reactive, but they will react with acids such as hydrochloric acid. So if you remember our example from the previous slide, we showed tin reacting with hydrochloric acid, whereas calcium would react just with water. Tin, you have to go to a stronger reactant, hydrochloric acid, to have the same kind of reaction. That's because tin is a less active metal than is calcium. Now at the very bottom set, you have copper, mercury, silver, gold, and at the very bottom is gold. Now that set of four, and there's maybe a couple others, but that set of four metals are what are called the noble metals. Sometimes they're called the coinage metals. We make jewelry, we make coins out of gold and silver and copper at least. Now mercury is a liquid, so you're not going to make jewelry or coins out of mercury, obviously. So copper, silver, gold, platinum, you could add to this list, are what are called coinage metals or noble metals. They're very unreactive. They will not react with hydrochloric acid. Some of them will react with oxygen. That's why silver will tarnish. If you have any silver cutlery, you notice that you have to polish them every once in a while to remove the silver oxide, the oxidation product. So they will react with oxygen, but they will not react with water or acid. They are the least reactive of the metals. So this is the activity series of metals. Basically what you need to recall is that there are three groups. The very reactive ones, sodium, potassium, lithium, calcium. The very unreactive ones, the ones we make jewelry out of in coins like copper and silver and gold. And then the ones in the middle, like magnesium, aluminum, zinc, iron, tin, lead. And there are a few others, but they're also sort of mostly right in the middle. And if we have any problems involving difference in the activity of metals, we will make sure that we compare within these three groups. Turning to the halogens, the most active halogen, as you might have guessed, is this very, very reactive fluorine. Fluorine wants to become reduced to fluoride. It wants to grab somebody else's electrons, right? So it's the most reactive of the set of four. Iodine is the least reactive of this set. And so any type of halogen displacements would be determined by that order of reactivity. Okay, we'll stop at this point, and in the next slide we'll begin to talk about stoichiometric relationships in chemical reactions. That's going to be fun. See you in a while.